Okay, good afternoon, everyone. Welcome to our today's coffee talk. We are honored to have Alessandro Nettis with us, who will be presenting his research on probabilistic traffic load assessment of prestressed girder bridges considering cross-section evolution. It's a long name. And now he's a PhD student at the University of Bari, Italy, and focusing on structural engineering. Now he is currently spending a 3 months visiting period at the UBC Barcelona to further his research. Okay, let's welcome Alessandro Nettis.
Yeah, thank you for the thank you for inviting me. Well, so I'm here to talk to you a little bit about bridges today. I know that this is maybe not one of the most common topics here, but actually I'll try my best to make it as clear as possible. Maybe with also some maybe some easy comparison also. Let's look at this. I want to start talking about a little bit of background. I don't know how many of you know about one of the biggest problems we have today in Italy with our facilities, our structures, actually our bridges, because lots of them are getting old and are having problems with degradation today. Actually, this is because most of them were built during 60s, 80s of last century. That's why now they have like more than 50 years of service life. So there's lack of maintenance also for them. So this is a problem we have in Italy. And actually, maybe most of you knows about the Polcevera Bridge failure, one of the biggest catastrophic events we had in Italy in recent years, in 2020 in Genova. There were like 43 victims, if I'm not wrong. And this event raised the attention of this problem a lot. So now universities, government, researchers are working on this topic here. Actually, this was just the last of these kind of events we are having in Italy, because actually there has been like former events like this one in 2017 and other ones which I didn't report in here, but actually we had this problem. It's a big problem. Most of the bridges we have in Italy are like that one you can see in the picture there. They are called prestressed concrete girder bridges. This kind of bridges, this bridge class, let's say, is one of the most widespread in Italy because actually it's so easy to build, to be built, let's say, for the construction. And in those years of this economic boom we had in Italy in last century, were so spread. That's why we have lots of them. And we need to assess them, actually. How does prestressing technique works? For the one of you that doesn't know, for example, I reported here just a simple picture. You have like a steel tendon, which goes inside the beam. With this steel tendon, which is steel cable, you are able to compress your concrete beam. If you compress this, your concrete material, which is one of the most widespread material of construction, behaves really, really well. So concrete behaves really well in compression and really bad in tension. So you want it to be compressed. And you can give your compression with this steel tendon, which goes inside your beam. As you can see here, when you apply the compression, you give like counter deflection to your beam. So you have like an upward deformation. And in this case, with this upward deformation, you can put a load on that. And actually, your concrete behaves really, really well. And let's say enhance its performances. So it's clear. The prestressing techniques, is it clear for you? Yeah. So I can go on. So we have this problem. So let's think maybe we can suppose to be one of these infrastructure network managers. I think we would not be happy to be one of them because actually they're facing now a very big problem in Italy. They have like hundreds, thousand structures to assess. And it's not so easy. It's impossible to have a detailed assessment of these kind of structures, of all of them, actually. We don't have human resources. We don't have time to do that. We don't have money also to do that, enough money. So, for example, if you can think, you are having, like, for example, the next week, lots of things to do, and you are sure that you will not be able to fulfill all of them. Maybe the best thing you can do is to think about, establishing some priorities in order to do your priorities first, and then go for the secondary, let's say, things to do. So actually, this is one of the best techniques also to have this kind of very large assessment. You can establish priorities first, and then you can focus, once you have your priorities, you can focus your, let's say, money, your resources, just on those ones, with your detailed assessment, for example. So you need a process to optimize your allocation of resources. How to identify priorities? We are studying that in Bari actually now. We are studying a procedure to do that. And well, this procedure needs to have three characteristics, basically. Has to be automated, has to be simple, and has to be efficient. Those three ones. Why simple? Because you are dealing with thousands of analyses. So when you're dealing with this big amount of analysis, for sure, you need the analysis to be simple, very fast in terms of computational cost. And actually, what you want to do is to avoid finite element analysis for this kind of assessment. You want your analysis also to be automated for the same reason, actually, because you have a very big amount of analysis to do. But when you gain in simplicity for your analysis, maybe you can lose precision. So you need also this analysis to be efficient. You need these outcomes to be meaningful, and also user-friendly, because the outcomes of these analysis needs to be used by managers, which maybe are not engineers, not scientists, and stuff like that. So well, you need this to be simple, efficient, and automated. We focus, so far, we have focused on this particular class of bridges, as I told you before, bridges like that with longitudinal beams and transversal elements that have the function to simply, let's say, get the beam together in their response to the loads. So, of course, we are dealing with traffic loads in this procedure, because actually it's one of the most common loads for a bridge. In this case, we are dealing with degradation also. So we have to introduce the model of degradation inside this procedure. And actually, let's think, for example, to an assessment of a structure for a professional engineer. When you have to do an assessment, normal assessment, let's say, you have to go there, you have to look at your structure, you have to make a survey in order to know your materials, the mechanical characteristics of these materials. You have to know, for example, the geometric characteristics of your structure in order to model it for finite element modeling, for example. You need to do that. But actually, for this kind of very big analysis of portfolios of bridges, you cannot do that because you don't have the time to do that. So actually, you need to deal also with uncertain quantities like this. For example, you don't know your mechanical properties, you don't know your geometric, for example, the thickness of the slab, the height of the beam, you don't know you have lots of uncertainties, let's say. So you need to introduce your uncertain quantities as random variables here. You need to deal with probabilistic distribution, and with some statistical techniques, you can generate, let's say, a sample of different realization of your structure. So it's not a structure anymore, deterministic structure, let's say, but it's like a sample of different realization of the same structure. We are working on that. That's why I call this probabilistic traffic load assessment, because of this. So I'm not going into the details of the analysis because actually we don't have the time, but just to give you two highlights of that. The first one is the main novelty of the analysis, which is the corrosion modeling here. What's corrosion? Actually, the corrosion acts on steel tendons, which is inside the beam. So acts on steel. And what does it do? It literally eats the external part of the steel. So you cannot account for the entire cross-section area of your steel rebar, but you have to reduce it for sure when you have corrosion. So we are dealing with, for example, in this case, we do the corrosion modeling with steel tendon area percentage reduction. And as this percentage reduction increase, you have to also modify the mechanical characteristics of your steel. So in this case, we are focusing just on the corrosion of the steel. And as you can see here in the plot, you have like the stress-strain relationship for the steel, which is inside the modeling. Actually, this is for zero corrosion value. So you have this one on the top left, which is the normal one without any modification. You have this that is called the elastic branch, the first one. This is the plastic branch, the second one. And you can, let's say, compute the deformation and the tension. Every point of this tells you which is the deformation of the, let's say, of the steel, and which is the, let's say, correspondent stress inside steel. So increasing corrosion, for example, 5%, 10%, 15%, and on, you modify this kind of law, let's say this relationship, and actually what you are going to do, you are going to reduce your ultimate deformation, your ultimate strain here. You're going to reduce your ultimate strength also, and you're going to reduce also the slope of the elastic branch. It's very, very slight, but actually is there also. So also the stiffness of your steel is changing, not only the ultimate properties, let's say. For example, at 10% of corrosion, you can see there's the completely loss of the plastic branch. You don't have it anymore. So this is the way to model corrosion in this that we are adopting in this procedure. And another highlight is the fragility curve construction. Actually, the output of this procedure is a fragility curve. What's a fragility curve? Fragility curve is a mapping between this parameter alpha here, which represents the intensity of the load, and a probability of failure of your structure. So you have like for a when you, for example, are fixing an intensity of the load here, for example, here 1.2, you can see in correspondence of 1.2, you have like about 40% of probability of failure. How do we compute these sets of data? This parameter alpha here is multiplying, is an amplification factor for your Q here, which is the traffic load actually by Italian standards. So NTC 18 are the Italian standards. This is the traffic load for the Italian standards, and you are multiplying it by alpha, this parameter, which can amplify or decrease also your intensity of the load. So you fix this value, for example, here, as I told you, 1.2. And how do we compute the probability of failure? Actually, we have this sample of realization, as I told you before. And these sample of realization are different, let's say, realization of the same bridge. You can, let's say, put this load on every realization of that. You can count the number of failures, just computing the maximum demand in terms of bending moment at the middle region of the beam, and in terms of shear stress at the support region of the beam. So you have your demand in terms of bending moment and shear. You have your capacity, which is affected by corrosion today. In this case, of course, you make a comparison between the two. If the demand is more than the capacity, the realization fails. So you can count the number of failures between all your realization. You can divide that by the number of realization, and you have your classic definition of probability, let's say, because actually the number of failures over the number of the total realization are the probability of failure of your structure. So you can compute by increasing the load all these sets, all these data, let's say all these points. Once you have this set of data, you can fit them with a log normal cumulative distribution, and you got the fragility curve. So this is the output of the analysis. So, but now let's apply this analysis. Let's have an application of that. We want to see if it works actually. As I told you, the aim is to prioritize at the beginning, no? And I told you also, when you have lots of things to do for next week, for example, you have to establish some priorities. I don't know, maybe you can also, let's say, classify them. For example, you have to deal with the work, you have to deal with your friends, you have to deal with your sport, I don't know, whatever you want, but you can give priorities based on what you think is the best for you. For example, maybe, I don't know if it's more, if it's for how many of you, but for me, for example, one of the priorities is the work. So I go for the priorities like, let's say, the typology of my commitment, for which I give the priority is the work, for example. So you can establish priorities, you can establish typology to give the priorities. And actually, we can do the same for this kind of analysis. We can establish some typologies also in order to give priorities. Typologies belonging to this bridge class, let's say. So we are not dealing with specific structures, but with typologies. And so we are having a typological assessment, let's call it this way. Typologies are, let's say, obtained like that. You can differ based on the length of the span, so 30, 40, and 50 meters. And you can differ based on also the number of beams. You have like 3 and 4 beams. So by combining these two quantities, you can have 6 different typologies. And these values are very, very typical of these kind of bridges. So you can do that. So we will have like one typology and different realization of the same typology, as I told you before.
Sorry.
Yeah.
Someone want to join? Only.
Someone want to join? Yeah.
Thank you.
Yeah, for sure. Okay. Let's go on. Let's look at the results of the application on these 6 different typologies of this procedure. You can see here the outcomes are the fragility curves, as I told you before. I reported here just for an example to look if the outcomes of the procedure are meaningful. I put here the 40 length span typology for the 3 beam typology and the 4 beam typology. These are the 2 plots. You have like 5 different fragility curves, because you can see the black one is for 0 corrosion value. And then as the corrosion increases, you have that this fragility curve moves on the left, because actually the probability of failure is increasing. And when the probability of failure increases, you have this movement on the left. If you look, for example, at alpha equal to 1 in this case, actually, what does it mean? Alpha equal to 1 means that you are multiplying the code conforming traffic load by 1. So you are taking exactly the code conforming traffic load. For that, you can look at this bar plot here on the right. You have that for 0 corrosion degree here, you have 0% of probability of failure. So you have that this kind of bridges, this typology of bridge actually is adequate to the Italian standards, because you have 0 probability of failure. But actually, when the corrosion degree increase, you can see there's a big increase in the probability of failure. So this shows you that the corrosion is having like a heavy impact on this kind of structure, is affecting a lot the behavior, and actually is very, very bad for this kind of structures, having corrosion on the tendon inside. This is one of the outcomes, but that one, maybe it's not, let's say, useful for prioritization. So let's look, for example, if the outcomes of this procedure can be helpful, can be of support for these let's say, poor road managers we have today in Italy. Because actually, we can do something also about that. If we analyze these three plots here, are the three outcomes for the 4-beam typology, 30, 40, and 50 meter span length. You can see, if you look at the decrease in the median of the fragility curves here, so 50% of probability of failure, it's the median of this probability distribution. If you look at the decrease in the median for increasing of corrosion degree from 0 to 15%, you can see, for example, here that the 30 meter span length typology has like 50% of decrease in performances, while the 50 meter span has a 30% of decrease in performances. So you can see from this bar plot here that actually the most vulnerable to corrosion is the 30 meter span length one as typology. So this is the one that suffered the most, this kind of, let's say, external action, this kind of hazard. And so these outcomes can be useful for prioritization, because actually you can focus on that one first and on the other one.
Sorry,
Yeah.
why is the 30 meter more vulnerable?
So in this case, the explanation can be related to the kind of procedure we are implementing. Actually, is related to the way of modeling corrosion, but also to the way of modeling the variation in the beam height in particular, in this case, and also which is related to the span length. Yeah, especially, and is related, of course, also on the, let's say, the computation algorithm for computing the flexural capacity in this case. So, for example, this kind of, let's say, this kind of typology is the one that suffered the most the flexural behavior, more than the shear one. Okay, based on how we model in this case the flexural behavior, the corrosion is affecting more the flexural behavior than the shear one. Okay, given that this typology here suffered the most the flexural behavior, is the most affected between the three. So it's something related to the model, for sure, in this case. And actually, yeah, I think it's something, yeah, it's an outcome because actually this way of modeling the flexural behavior and the shear behavior are the ones that are used also by professional engineers, so in real world. So actually this is, yeah, a consequence of the modeling, but actually with the instrument we have today, with computing this kind of behavior, it's like that. When you do an analysis, it behaves like that. For sure, there can be some improvements in shear behavior, in modeling shear behavior, especially because we don't have too much, let's say, analytical model for that today. So maybe finite element modeling could be an improvement from that side. And I'm working on that. Actually, now here in Barcelona, I worked on that. And for sure, this outcome can be improved, let's say, yes, with finite element modeling, we can improve it. But actually, it's, you know, it's an indication. It's an important indication. This one. Is it clear? Is it good? Yeah. So this is, I think, the last slide on results. So we can do some prioritization among different typologies of bridges with this procedure here. But actually, maybe if you look better at the results, we can do also something else, which is also these outcomes is interesting, I think, because actually we are able to compute fragility curves with this procedure, but not considering both shear and flexure failure mode, but actually taking them one by one. So we are just considering flexural failure mode and we can compute the fragility curve just for flexural failure mode, and we can compute also the fragility curve just for shear failure mode. So taking them one by one. The dashed one is for flexural failure mode. The pointed one is for shear failure mode. Maybe it's better to look at this bar plot here, especially here and here for zero corrosion value. These are the outcomes for 40 meters and 50 meters span length. If you look here, for example, at zero corrosion value, if you look at the median of this fragility curve, you can see that you have in cold color, let's say the shear one, and in hot color, the flexural one. You can see here that the median of the shear fragility curve is lower than the flexural fragility curve. What does it mean? It means that, for example, in this case, at zero corrosion value, so no degradation, the dominant failure mode is the shear one, because it's the most vulnerable in this case. And the shear one, actually, as I told you before, happens in the support region of the beam. As corrosion degree increase, you have here, for example, that the median of the flexural failure mode is lower than the shear one. So with corrosion degree, as I told you also before, as corrosion degree increases, flexural failure mode is the most affected. So it's the most probable also for these kind of, also for the 30-meter one actually is the same. That's why I didn't put it here. You can say that this is the most probable, and it happened in the central region of the beam. So as I told you at the beginning, these structures are a little bit particular because you have these internal tendons, which is very, very important for them. But it's internal. It's something, if you want to go there and make a survey on this kind of structure, it's like you have to make a survey for your bone, for example, on your arm. You cannot see it from the external side. You have to use some particular techniques like X-ray or stuff like that. So these techniques are more expensive than the ordinary one. So if you can, let's say, prioritize also this kind of special inspection, for example, by focusing just on the middle region, when you know that you are in presence of corrosion, this can be good also. This can be interesting also as an outcome. So yeah, I think that from the part of the results is we are done, and we can conclude with some, well, to sum up something with some concluding remarks, because I want you to, let's say, have in mind just 2-3 general ideas about this work we are, let's say, doing in our Polytechnic University in Bari. We are trying to develop like an automated, simple and efficient procedure for this kind of, let's call it, portfolio scale bridge analysis. So very, very big analysis. The aim is to establish priorities. In this case, for optimization of resources. We are studying now this bridge class, simply supported, girder-type, post-tension, prestressed concrete bridge, which are the bridges I showed you before during the presentation. And well, because it's one of the most widespread we have in Italy, typology we have in Italy, but actually this kind of procedure can be extended also to other typology of bridge. And well, the main outcomes are, of course, that corrosion for these kind of bridges is very, very dangerous. And that this procedure, of course, it has to be improved, has to be, actually, as I told you before, I'm working on that to improve it with finite element modeling to validate it, stuff like that. But actually can be helpful in prioritizing among different bridge typologies, and also in prioritizing interestingly in spatial inspections. Well, I'm done. If you want to know more information about that, we published a paper on that. You can check if you want. The procedure is very detailed on the paper, so if you want to check, just ask me. Yeah, thank you very much. If you want to ask me something. Yeah.
I'm not sure I understood the methodology correctly.
Yeah.
So you decide on a total load, you apply it to your bridge, you distribute it differently, that total load,
I didn't tell you how the load is distributed between the beams, actually, because it's too technical, but actually, yeah.
And then you check maximum shear, maximum bending.
Yeah.
You compare it to when it breaks, and you have a sample size, and when it breaks, that's the probability.
Yeah, for that one. Actually, I can show you. Yeah, I didn't report so much detail about that. Actually, that's why maybe this is not so clear. Actually, you have different realization of your bridge typology, let's say. So by changing the mechanical properties, by changing geometric properties and stuff like that, you can generate a sample. In this case, for example, there are 350 different realizations for one typology. Okay, so you have
typology is
let's say
span and
a number of beams. Exactly. Let's say you have a structure with 30 meters span length and 4 beams typology. Okay, FOB. Okay, let's think about that. And you have 350 different realization of these structure by changing.
What is a realization?
It's just a model. Let's say that is a model. It's like you want to have, like, for example, your concrete strength for that kind of structure can be 30, 35, and 40 megapascals. Okay, so you have 3 different possible values for your concrete strength for your structure. You can generate 3 different realizations of the same structure by changing these characteristics. Okay, so you have 3 different realizations of that, 3 different models, let's say, of that. Then you can say that also your steel strength can be, for example, 1,600, 1,700, 1,800 megapascals. So you can generate in this way 9 different realizations by combining the 3 and 3. I think there are 9. Yeah, I think there are 9. By combining the 3 steel strength and the 3 concrete strength. Okay, let's imagine to do this for, in this case, we have like 11 uncertain quantities. And we have probability distribution for each of these 11 quantities. So you can generate lots, thousands of realizations of the same structure. With these statistical techniques, you generate random samples of just one structure. It's like you have 300 different models of the same structure. Is it okay?
Yeah, I think
so once you have these 300 different models, you can put the same load on each one of them. As they are different, they will have like a different capacity. Okay, so the demand, by comparing the demand, so the load, let's say the stress and the capacity, you can, for example, check if the demand is more than the capacity for each of these one realization. It's okay. If, for example, over 300 realization, you have that, let's say, 50 fails, you have 50 over 300 failures. So your probability of failure will be 50 over 300. Is it clear? Yeah.
I think so.
Yeah.
So for a given corrosion, you can have different
You have to repeat this for a given corrosion value, which can affect the capacity. So 0, 5, 10, 15, and 20% of corrosion. You have to repeat this for all your realization, and you have to repeat this for all these different values of load. They are like 10,000 analysis, 100,000 analysis, I don't know. That's why you need this to be very simple, the model to be very simple. You can solve it. Actually, you can solve this analytically. So it's really, really simple.
One last question. Yeah. Where does the uncertainty in the material parameters come from?
The uncertainty in material parameters, we took the probabilistic, let's say, distribution of the parameters by literature. There are in literature this kind of, let's say, papers where they, let's say, collect data by different bridges in real world. So you can have, like, for example, one bridges that were built with some particular concrete, one bridges for another, one bridges for another one. So they had like a very big survey on bridges all over Italy. Also, these data are from Italy, because actually the analysis is in Italy, but also in Portugal, if I'm not wrong. Data comes from Italy, Portugal, I don't remember, maybe Spain also. Yeah, so from different regions, you can generate this very big amount of data, and you can compute your probabilistic distribution of this, because actually concrete is affecting also, the strength of concrete is affecting also by the degradation in time. So you can have maybe, for example, at the beginning, when you cast it, you have like 30 megapascals, and after 10 years, you have 25, because it can change also over time. So they made this collection of lots of data for strength of concrete, but it's the same for the steel, it's the same for, I don't know, for other uncertain quantities, for example, that we didn't know. For example, the thickness of the slab, actually, you don't have like a probabilistic distribution for that. So you can just put, let's say, minimum value, a maximum value, and you can use a uniform distribution. So you can do lots of things in order to model this uncertainty, let's say. And yeah, the variation comes from that. Thank you. Questions? Yeah, something.
Which are the 11 variables that you are considering?
Yeah, so I try just to remember. Beam height, first one, which is related to the length of the beam. Okay, there is a
So
relationship.
you are relating the height.
It's like a regression model. It's like a regression, yeah. Because actually, when you design it, your beam height depends on the span that you have to overpass, let's say. Beam height, thickness of the slab is the second one. Thickness of the road pavement, because actually is the load that the permanent load that acts on your structure. There is steel strength, concrete strength for sure. There is also mild reinforcement steel strength, which is not the tendon one, but actually the normal steel that you put on reinforced concrete structures. The modulus of elasticity of the steel. And if you want to know all of them, let me check, because actually I have it, of course, in the paper.
But let's say that you are modifying the properties of the materials and then the geometry of the
properties of the material and geometry. Basically that one. Yeah. And actually, you have also for sure the quantity of the steel inside beam. That is also related to, because it's like a designed property, so it's also related to the beam length and to the beam height. So we have like independent random variables with probabilistic distribution and dependent random variables with linear regression and stuff like that. So you have that. Actually, yeah, there are other 2 or 3 variables, but yeah, actually it's all of these for sure.
Can I ask about the material model
Yeah.
that you commented on before?
Yeah. Okay. This one.
Yes.
Yeah.
It seems to me that mainly the effect of the corrosion is that it increases the brittleness of the material.
Yeah, exactly.
So you also commented, and you have written the area of reduction of, where is this intervening? The reduction in the area of the tendon.
In the, let's see, the algorithm for computing the capacity, actually. I didn't put them here, both for the flexure and for the shear. The shear is a very simple formula. And actually, the corrosion is acting for shear just on the state of the mean state of compression of the beam. So actually that one is the only thing that counts for the shear failure. So if you have like the reduction of the steel tendon here, you have the loss of the correspondent loss of compression, of mean compression. And so the only thing that is affecting the shear is that one. While for the flexural bending moment is more complicated. We have an entire algorithm for that written on Python by coding, and yeah, actually all is based on the translational equilibrium of forces acting in a cross section of the beam. So you have like the compression in concrete and the tension in the tendons, and like if you have like a reduction of the area and the reduction also of the characteristics of the tendon, you have that your, let's say, resultant force in tension has to be let's say modified by those kind of characteristics by corrosion. Yeah.
But
Yeah.
it's what I do not understand is the reduction of area is not affecting the Young modulus of.
No, no, these are two different things. We are considering both of them, but with different things. So we have the area reduction, and then the this way of modifying these mechanical properties. This is a model study. Actually, the name is of the paper is EU. It's a Chinese one, it's a Chinese guy. Actually, there are others in Italy that are developing today. And yeah, they like made some experiments on corroded rebars, corroded reinforcing steel, to let's say have this analytical model for the modification by the corrosion degree. Yeah.
This is what they obtain.
This is what they obtain actually. Yeah, there are two different laws modifying by the corrosion, the elastic and the plastic. So at first the reduction of the ultimate and the yielding point also here. And then at a certain values of corrosion, which can change, it's not always 10%, but can change actually. You have the completely loss of the plastic part, so you don't have like a ductile failure anymore, but you have just a brittle failure. And you have also the changing of the stiffness after that. Yeah.
Thank you.
Thank you.
I think maybe we can stop our session. Let's thank Alessandro again.
Thank you.